Welcome back to the Deep Dive, where we take the high-velocity flow of information and distill it down into the core knowledge you need to be truly well-informed.
Today, we're tackling a big one.
We really are. We're diving deep into probably the most complex, high-stakes area of enterprise tech today. Data protection in a cloud world that's defined by, well, this clash between global reach and local law.
It's a fascinating conflict, isn't it? I mean, for decades, security was, sort of simple.
Right? Build a big wall.
Exactly. Build a robust perimeter, set up your firewalls, manage user passwords. But now, with data streaming everywhere, living in multi-tenant cloud environments, constantly crossing borders, those old perimeter defenses are just not enough.
Absolutely. The whole challenge has shifted, hasn't it? It's moved from keeping the bad guys out of the network to keeping the bad guys out of the data.
Yes. Even if they already have admin access to the server itself.
That's the key. So today, we have to protect data when it's stored, when it's moving, and this is the really tricky part, when it's actively being used by a CPU.
And that huge technological challenge is just compounded by all this legal complexity. The global nature of the cloud means your data might be physically stored in Dublin.
Sure.
But the corporate HQ of your cloud provider is in Seattle. And the actual person the data is about lives in Berlin.
So you have this borderless infrastructure just running headlong into these increasingly strict local jurisdictional demands, things like GDPR, or these new localization mandates.
That's the collision.
Okay, let's unpack this, because getting this legal landscape right is really our mission for this deep dive. We need to clearly distinguish between physical location and legal authority, these often confused concepts of data residency and data sovereignty.
Right. And once we lay that legal groundwork, we can look at the technical response.
And that's where it gets really interesting. We're going to do a detailed exploration of the 3 stages of encryption and then dive deep into how technologies like Always Encrypted with secure enclaves and policy as code are finally giving organizations a real path to, true enforceable jurisdictional compliance.
Let's do it.
So we have to start here. If you confuse data residency and data sovereignty, your entire compliance strategy is basically built on shaky ground. Let's tackle a physical part first, data residency.
Data residency is, thankfully, the simplest concept to grasp. It is strictly an infrastructure decision. It's about the physical location, the literal country, region, or specific data center facility where your data bytes are stored on a disk.
So it just answers the question, where is the server located?
That's it. Pure and simple geography.
And organizations choose these regions for a mix of reasons, right?
Yeah.
It's not always just about compliance.
No, not at all. I mean, compliance is a huge driver, of course, but operational efficiency usually comes first. Low latency is king.
Makes sense.
If your end users or your application servers are physically located in Southeast Asia, you need a data center presence in Singapore or Hong Kong to minimize that network delay and give them the best possible experience.
And I've also heard about decisions based on sustainability.
Oh, absolutely. We're seeing that more and more. Choosing data centers that run purely on renewable energy or focusing on regions with, strong political stability, it's all part of that strategic placement decision.
Okay, so residency is the foundational layer. And a lot of national and industry regulations start right there, demanding that data be physically stored inside the nation's borders. Can you give us some of the key examples we see globally?
Sure. Residency mandates are very common, especially for sensitive sectors. Take Australia's APRA regulations, for instance.
For finance?
For finance and certain types of healthcare data. They impose really strict requirements, often demanding that data be stored domestically. Or look at Canada's provincial laws.
Like in British Columbia.
Exactly. British Columbia's FOIPS, that's the Freedom of Information and Protection of Privacy Act, it requires that public sector and health data must be physically housed within Canada. So to meet these, the organization has to deploy specific infrastructure only in those approved regions.
Okay, so that satisfies the geographical mandate. But residency alone doesn't solve the problem, because the where doesn't dictate the who controls it. And this is where the real tension begins as we move to data sovereignty.
This is the crux of the issue. Data sovereignty is the principle of legal jurisdiction. It says that digital data is subject to the legal framework of the country where it resides, or, and this is the key complexity, the nationality of the data subject.
So it defines which government, which court, Which legal entity has the authority to compel access to that data?
Regardless of where the bits and bytes actually sit.
And this is where global companies just run into chaos. You meet the residency requirement, you put the data in country A, but you're still subject to the laws of country B. How does that structural overlap actually play out in the cloud?
The prime modern-day conflict example is the U.S. Cloud Act.
Right.
Imagine a European company subject to really strict EU data laws. They decide to store their customer data in a facility in Germany using a US-based cloud provider.
Okay, so residency is covered, the data's in the EU.
Residency. Check. But sovereignty is now in question because that cloud provider is subject to US jurisdiction.
And what does the Cloud Act allow U.S. authorities to do in that situation?
Well, the Cloud Act, the Clarifying Lawful Overseas Use of Data Act, it allows U.S. federal law enforcement to compel U.S.-based tech companies to provide requested data. And this is the key part, regardless of whether that data is physically stored in the U.S. or in an overseas data center.
Wow. So a warrant issued in the U.S. could legally require the provider to hand over data stored in Germany.
Exactly. And that could create a direct conflict with German or EU law.
So that is the core difference. Residency is satisfied by the physical storage location. Sovereignty is threatened by the legal jurisdiction the cloud vendor is primarily subject to.
You've got it. And GDPR is the classic example of a sovereignty requirement that goes way beyond residency.
How so?
GDPR doesn't strictly say you must store this data in Europe. What it says is you must protect EU citizen data with appropriate safeguards, regardless of where it is physically located.
So that's why we hear so much about cross-border data transfers.
Precisely. If you transfer data outside the EU, you have to ensure that the receiving jurisdiction provides an essentially equivalent level of protection. That requirement for things like standard contractual clauses or SCCs and transfer impact assessments. That is purely about satisfying the sovereignty aspect, making sure EU legal protections travel with the data.
It's about guaranteeing legal control, not just physical placement. Okay, so if residency is the basic where and sovereignty is the who controls it, what happens when governments combine those into the most stringent mandate of all? And that's data localization.
Data localization is sovereignty taken to its most extreme. It demands not only local storage, so satisfying residency, but it also mandates local processing of the data.
And in some cases, it can go even further.
Oh yeah, in some cases it can even dictate that access, management, or even the staff involved in handling the data must be local citizens or locally certified entities.
That dramatically escalates the requirements for multinational companies. What are the key global examples forcing this level of change?
The two biggest examples are probably Russia and India. Russia's federal law on personal data mandates that all personal data of Russian citizens must be stored, processed, and even the initial collection has to happen on servers physically located inside Russia.
The initial collection, too.
Yes. You can't just route that data through a centralized global hub before moving it to Russia. The entire life cycle must adhere to that localization rule from the very first point of entry.
That's a massive barrier to centralization and global economies of scale. How does India's regulatory landscape compare?
India has proposed and enacted various regulations, often sector-specific, that require critical personal data, particularly in finance, to be processed only within India. This goes way beyond just storing a copy there. We're talking about dedicated, isolated infrastructure and sometimes even dedicated local regulatory reporting entities.
The operational burden, especially for high availability, must be staggering. I mean, how do you even handle disaster recovery under these rules?
And that's the operational headache. A standard global disaster recovery plan, a DR plan, might involve synchronous replication from, say, India to a nearby region like Singapore for immediate failover.
Seems sensible.
Under a localization mandate, that failover is often a direct compliance violation.
Because the data is now being processed outside the country.
Exactly. The data payload, even if it's an encrypted copy, is now being processed and stored outside the mandated jurisdiction.
So you can't use your global redundancy pool. You have to build in-country redundancy.
Precisely. You're forced to build redundancy, sometimes even tertiary redundancy, entirely within that sovereign border, and that dramatically increases your cost, the complexity of your networking, and your total operational footprint. Localization basically requires organizations to build completely isolated sovereign cloud regions inside the existing global hyperscaler environment.
It's a total architectural change, which really proves the necessity of these higher-level controls we're about to get into.
It really does.
Okay, so we've established this complex legal map. To navigate it, especially that thorny issue of sovereignty. We need technical controls applied universally. The defense system has to protect the data at all times. This brings us to the three pillars of encryption, starting with the baseline, encryption at rest.
Right. Data at rest is the passive data, so information that's just sitting on storage devices like disks, database files, tape backups, or archival storage. In Azure, the baseline defense here is 256-bit AES encryption, which is a very powerful industry standard.
And what are the main services that enforce this baseline protection within the data stores themselves?
For databases, the key technology is transparent data encryption, or TDE.
TDE?
TDE is a fantastic layer of security because it encrypts the entire database, the data files, the log files, and crucially all the backups at the page level in real time. And it's totally transparent to the application.
So the app doesn't even know it's happening.
Correct. In new Azure SQL databases, TDE is enabled by default. It provides that essential security baseline, ensuring that if someone physically steals the disk or the backup tape, the data is just cryptographically useless to them.
Okay, so TDE handles the database files. What about generalized storage? Things like blobs, files, data lakes.
That's handled by Storage Service Encryption, or SSE. SSE automatically handles the encryption of data in Azure Blob Storage and Azure File Shares. It's integrated deep into the service itself, encrypting the data before it's written to the disk and decrypting it when you retrieve it. It's basically a mandatory function of the storage platform now.
You mentioned disk encryption for virtual machines for VMs, and I think you said a key older technology, Azure Disk Encryption, or ADE, is on its way out. Why is that, and what's replacing it?
That's right. ADE, which relied on technologies like BitLocker or DEncrypt inside the guest operating system, is scheduled for retirement on September 15, 2028.
And the reason for the shift?
It's about depth of protection. The recommended successor is encryption at host. Instead of encrypting at the OS level, encryption at host uses the hypervisor itself to encrypt data as it flows from the VM down to the storage media.
Why is that a strategic improvement? What does that get you?
It creates a deeper security boundary. It essentially removes the decryption point from the storage controller itself. And here's the really strategic point. Encryption at host protects the data, even if that virtual disk were somehow exported out of the Azure environment for maintenance or some administrative reason.
So the encryption stays with the data.
The encryption stays with the data, protected by keys stored in the platform. It secures the data against a much wider array of attacks that might be able to bypass OS-level encryption.
So protection is no longer some optional add-on. It's baked right into the architectural decisions of the platform. Okay, now we move from protection to control. Key management and sovereignty, level 2. This is where that sovereignty discussion really kicks in again.
Absolutely. The decoupling principle is fundamental here. The encryption key is the ultimate secret. It must be stored separately and managed distinctly from the encrypted data itself.
Because if you control the key, you control access to the data.
Exactly, regardless of where the data resides or who manages the physical server.
And this allows an organization to prove, both contractually and cryptographically, that a foreign government can't access the plaintext without the organization's direct involvement. So walk us through the three levels of key ownership in the cloud.
Okay, the default is Microsoft Managed Keys, or PMK. With this, Azure manages the entire lifecycle generation, rotation, storage, access. It offers really low operational overhead, it's easy to use, great performance, but it provides the lowest level of sovereignty assurance because, well, Azure holds the keys.
So for high compliance scenarios, we have to jump to the next level, Customer Managed Keys, or CMK. What are the operational realities of adopting CMK?
CMK is the mechanism for achieving what we call Level 2 sovereign control. Here, the customer takes full accountability for the cryptographic keys. You define the rotation schedule, you manage the access policies, and you are responsible for the keys' availability.
And these keys are stored in something like Azure Key Vault.
They're stored in a key management service like Azure Key Vault or KV, or for even higher assurance, the Managed Hardware Security Module, the Managed HSM.
Okay, why would I opt for a Managed HSM over a standard Key Vault? What's the difference?
Managed HSM is really the gold standard for CMK. It's a single-tenant, highly available FIPS 142 Level 3 validated hardware device. The critical distinction is that the keys never leave the protected physical hardware boundary.
Never.
Never. They are created, stored, and used only inside the HSM. This provides a vastly superior audit trail and cryptographic assurance, which makes it essential for the most stringent sovereignty requirements, particularly in finance and government.
I can imagine the operational complexity and the risk. increases dramatically with CMK, even with managed HSM. If the customer messes up, what happens?
The risk is total data loss. I mean, if you, the customer, accidentally delete or lose access to your CMK, you have essentially rendered your encrypted data permanently inaccessible. Microsoft cannot help you recover it.
Because they never had access to the key in the first place.
Exactly. And that's the trade-off for sovereignty. Maximum control equals maximum responsibility.
And finally, the highest level of control, which I hear is rare. Hold your own key, or HYOK.
HYOK is the ultimate geopolitical hedge. It means the cryptographic keys are not just managed by you, the customer, but are physically held completely outside the cloud provider's premises, often in your own on-premises HSM or key management system.
So if a government issues a compulsory access order to the cloud provider, the provider can genuinely, truthfully say, we physically do not possess the means to decrypt this data.
That's the idea. It offers the absolute highest legal and cryptographic separation. But the trade-off is severe. It adds significant complexity, it introduces latency and key access, and it can potentially impact the service-level agreements, the SLAs, of the services that rely on those external keys.
So it's only for the most sensitive data imaginable.
Exactly.
Okay.
The most politically sensitive or highly regulated data.
That really puts a control layer in perspective. Okay, now that we know how to secure data when it's still, let's pivot to the third pillar. Encryption in transit, protecting data when it's actively moving across wires.
Right. Data in transit is everything moving between endpoints, from your browser to the web server, from the web server to the database, or even between data centers. And we have to defend this at multiple networking layers.
We all know the standard protection at the application level, layer 7. What are we enforcing there?
At the application or transport layer, the standard is the use of TLS 1.2 or later transport layer security. This ensures that client-server communication is encrypted end-to-end. All public endpoints across Azure mandate strong, modern TLS versions. And you should always be enforcing HTTPS for web traffic, often using something called an HSTS policy to make sure browsers never even try to connect insecurely.
That's vital for protecting traffic outside the data center. But let's go deeper into the physical wires running between the cloud provider's massive data centers. If customer traffic is moving across fiber within the cloud backbone, what protection is there against a really sophisticated physical attack, like a wiretap?
This is a critical and often unseen control that addresses a major zero-trust principle, which is you trust nothing, not even the provider's own network. When customer data moves between Azure data centers, so outside the immediate boundary of single facility, we enforce Layer 2 encryption using MACsec.
MACsec. Tell us what that is and why it matters at this deep infrastructure level.
MACsec stands for Media Access Control Security. It's hardware-level, point-to-point encryption that's applied directly on the underlying network hardware, the routers, and the switches. The packets are encrypted before they even leave the network device and are decrypted only when they arrive at the next trusted device. It's a cryptographic guarantee at the data link layer.
So even if an advanced attacker managed to physically tap into the fiber optic cables running underground between two Azure regions,
all they would intercept is encrypted network frames. Garbled nonsense. It prevents physical snooping and man-in-the-middle attacks at the infrastructure level. This is active on by default protection for all Azure traffic traveling on the Microsoft network backbone, whether it's within a region or across continents.
And finally, how do organizations ensure their connections back to their on-premises network maintain this level of confidentiality?
For connectivity back to your corporate network, you rely on secure tunnels. Most commonly, this is done with an IPsec VPN for site-to-site tunnels. For larger enterprises, they often use ExpressRoute, which provides a dedicated, private, non-internet connection.
But doesn't ExpressRoute by itself lack native encryption? I thought that was the catch, because it's a private line.
That is the catch. While ExpressRoute is logically private, it might travel across a telecom provider's network before it reaches the cloud endpoint. So customers often add security layers on top.
What are the options?
The two options are either layering an IPsec VPN on top of ExpressRoute, which encrypts the traffic at the IP layer, or leveraging ExpressRoute MaxiSec, which encrypts the connection at the physical cable level, ensuring end-to-end confidentiality from your on-premise router right into the cloud provider's network boundary.
And that decision is driven by how sensitive the data is?
Entirely.
Right.
It's all based on the sensitivity of the data traversing that private link.
We've established robust security for data at rest and data in transit.
Mm-hmm.
But now we hit the final, most sophisticated vulnerability, data in use. I mean, if the CPU needs to perform a calculation, say a simple salary aggregation, it has to first decrypt the data into plaintext inside the machine's memory. And that moment of decryption creates this window of vulnerability to memory scraping, sophisticated rootkits, or even malicious insiders like a compromised DBA or an OS administrator.
And this is where the concept of confidential computing steps in. It is the revolution that's required for true Level 3 sovereignty. And the database world really took the lead here with a technology called Always Encrypted.
Let's rewind to the original introduction of Always Encrypted, which came out with SQL Server 2016. How did this client-side technology try to close that memory vulnerability gap?
The original Always Encrypted was brilliant in its simplicity. It was a client-side solution. The application driver running on the client machine was the only thing that had the encryption key. Before any data left that client machine, whether it was a query parameter or data being inserted, it was encrypted.
And the database engine itself?
The database engine received the encrypted data, stored the encrypted data, and crucially, never possessed the key necessary to decrypt it. The DBAs, or admins, could look at the database pages, but all they saw was ciphertext.
So it provided a strong separation of duties. The DBA manages the database structure, but can't read the sensitive payload.
Exactly.
That seems like a complete solution, but you mentioned a critical limitation. If the database engine can't decrypt the data, how can it perform any complex operations on it?
And that was the Achilles heel. Since the data was encrypted, the computational capability was severely constrained. If you use what's called deterministic encryption, where the same input always yields the same ciphertext, you could only perform simple equality comparisons.
So you could ask, does this encrypted salary column equal the ciphertext for $50,000?
Right. But you couldn't ask which salaries are greater than $100,000 or sort this list of names alphabetically.
No rich queries at all.
No. For any of those rich computations, range, queries, sorting, pattern matching with you had to either use randomized encryption, which had even less support, or you had to bring the data all the way back to the client, decrypt it there, process it, and then re-encrypt the results.
Which just defeats the purpose and sounds incredibly slow.
It defeats the purpose, introduces massive performance bottlenecks, and makes it totally unfeasible for analytical workloads.
So the original AE solved the confidentiality problem, but it severely hampered usability. This leads us to the real game changer, always encrypted with secure enclaves. When this enhancement arrived, how did it fundamentally allow rich computation on encrypted data?
This arrived with SQL Server 2019 and is now pervasive across Azure SQL. The Secure Enclave enhancement introduces a trusted execution environment, or TE, directly into the database engine process, and that solves the computational limitation while maintaining the confidentiality guarantee.
Okay, explain this black box concept. How does the database engine delegate sensitive work to an enclave without compromising the key?
The Secure Enclave is a cryptographically isolated memory region within the CPU. So when a complex query arrives, say a pattern match on a protected name column, the database engine passes the encrypted data and the decryption key into the enclave.
And this key is only provided by the client application that initiated the query, correct? It doesn't live on the server.
Precisely. The client securely sends the key, and the database engine just acts as a conduit. The data is safely decrypted only inside the enclave. The computation, the pattern matching, the range check is performed on the plaintext. The result is then encrypted again, and the ciphertext result is returned back to the standard database engine memory.
So the OS administrator, the DBA, anyone outside that enclave cannot inspect the plaintext, even during actor processing. The enclave is completely opaque to the host environment.
It is the ultimate boundary enforcement. It's protected by the hardware and the hypervisor itself, acting as a cryptographic black box. This is the cornerstone of confidential computing architecture.
What are the primary types of enclaves we see being used to create this isolation boundary?
There are two main types supported. First, you have VBS enclaves, which use virtualization-based security, or VBS, and rely heavily on the Windows hypervisor. You can think of this as a software-enforced boundary.
And
The second, and what's increasingly common for maximum assurance, are Intel SGX enclaves software guard extensions. SGX is a true hardware-based TE, leveraging microarchitectural extensions in silicon itself to guarantee the isolation.
So SGX offers a higher level of assurance tied directly to the chip itself. What practical functions does this capability unlock for compliance and for database administrators?
The leap in functionality is vast. First, you get rich confidential queries, full support for standard comparison operators, sorting, advanced pattern matching, all performed on the encrypted column. But strategically, I think the biggest operational gain is the ability to perform crucial cryptographic maintenance operations on the server side.
You mean things like key rotation and the initial encryption?
Exactly. Before enclaves, if you needed to rotate a key, you had to move the entire encrypted column out to the client, decrypt it, re-encrypt it with the new key, and then push it all back. It was a massive, time-consuming operation.
Sounds like a nightmare.
It was. With enclaves, the database just delegates this rotation to the enclave. The data stays securely inside the database environment, the enclave decrypts and re-encrypts in its protected memory, and the new column encryption key is returned. This dramatically simplifies management while maintaining continuous confidentiality.
That significantly streamlines the compliance process. But let's pause here for the enclave reality check. Known limitations. This is advanced technology, and I know developers and DBAs need to be prepared for the trade-offs.
The trade-offs are significant and require serious database refactoring. The most critical restriction is architectural. Encrypted columns cannot be used in various structural definitions.
Like that, yes.
Specifically, they can't be used in clustered indexes, primary keys, PKs, foreign keys, EVKs, or unique key constraints.
Wait, why is that? Why can't the database use an encrypted column as a primary key? That seems fundamental.
The database engine uses primary keys and indexes to quickly sort, enforce uniqueness, and manage relationships. It needs to perform immediate, low-level comparisons and hashing on the raw data value to maintain that structure. The moment you encrypt the column, especially with randomized encryption, the database can no longer perform that function because the value is obscured.
So it would have to decrypt it every single time.
It would have to delegate every single index lookup to the enclave, which would just be prohibitively slow. So to adopt AE with enclaves, you often have to redesign your entire schema, removing these constraints before you can apply the encryption.
That is a massive project for any legacy system. Are there performance and query limitations too?
Yes. For example, while the like operator is supported, you can't use escape characters within it. More critically, historical performance limitations meant that only nested loop joins were supported when dealing with encrypted columns.
Has that improved?
It has. Newer versions like Azure SQL Database and SQL Server 2022 have made great strides in query optimization. But complex queries involving these columns can still introduce noticeable performance latency compared to plaintext data. You gain confidentiality, but you pay in query design flexibility and potentially performance cost.
These limitations really underscore that this is not a one-click solution. It's an architectural commitment. Let's connect this back to the highest level of legal assurance, Level 3 sovereignty, which is achieved through the broader concept of confidential computing and attestation.
Right. Confidential computing is the umbrella term for that Level 3 control, data protection and use. But if the enclave is a black box, how do you trust it? How do you prove, especially to our regulator, that the application running inside that D is exactly the one you intended, and that the hardware hasn't been maliciously altered by an insider or a rootkit?
That's the core question of zero trust, isn't it? Verify, then trust. And the answer is attestation.
Attestation is the cryptographic mechanism for verifying the integrity of the T. It's a process where the hardware or the hypervisor generates a cryptographically signed report or a measurement of the code running inside the secure enclave. This report proves the application's identity, its configuration, and the integrity of the underlying hardware.
So attestation is like a digital inspection. And what is the strategic payoff for having that proof?
The payoff is secure key release. This is the ultimate technical enforcement of Level 3 sovereignty. Remember our customer-managed keys stored in the managed HSM?
Yes.
We can now configure a policy on that HSM that says, I will only release this highly sensitive decryption key into a computation environment if that environment first provides me with a verifiable attestation report.
This means the key only unlocks the data if the computation is proven to be happening in that secure black box, which satisfies the highest regulatory bar.
Precisely. The policy might be enforced by a trusted key release service. It verifies the signature on the attestation report. It checks that the report matches a predefined integrity baseline, specific CPU microcode, specific OS patches, specific application version, and only then does it release the key.
And if it doesn't match?
If the T has been tampered with, if a single bit of memory has been changed, the attestation fails, the key is never released, and the sensitive data remains protected. This mechanism effectively removes the cloud provider's ability to access the data without the customer's cryptographic and policy-based consent.
We've covered the technical tools required to protect data at every stage. But none of this matters if you don't know what data you have, where it is, and how sensitive it is. This transitions us to proactive governance, starting with the strategic architecture of data discovery.
The reality is that the vast majority of organizations suffer from the visibility gap. Sensitive data PII, regulated health records, financial blueprints is often stored in disparate, unclassified repositories. This is the dark data problem. If you can't find it, you can't apply CMK or confidential computing to it.
So the first step is achieving continuous automated visibility across the entire data estate. How do we technically implement this discovery process across this complex cloud environment?
The centralized engine for this within the Microsoft environment is Microsoft Purview. Purview acts as a data catalog and a governance system. The process involves registering every data source, your SQL databases, your storage accounts, your file shares, and then initiating deep scans.
What exactly does that scan do? Does it pull the entire data set into Purview?
No, not necessarily. The scan typically extracts metadata and schema information, and then it uses deep analysis to automatically apply classifications based on built-in sensitive information types, or SIT.
And SITs are just patterns.
Their patterns, Purview recognizes think specific formats for credit card numbers, national IDs, or healthcare codes. The result is this beautiful map showing you exactly where your sensitive information resides across your entire estate.
And what's the recommended way to authenticate these scanners to all those diverse data sources securely? You can't be using passwords for this.
No, best practice is absolutely vital here. Use a managed identity, or MI, tied to Microsoft Entra ID. A managed identity is a security principle that's automatically managed by Azure. It eliminates the need for hard-coded passwords, rotation schedules, or storing sensitive credentials in plain sight.
So it reduces the attack surface.
Massively. It integrates the whole discovery process into your organization's zero-trust framework.
Right. Okay, so once we've classified the data, we need that classification to be persistent and enforceable, no matter where the data travels. This brings us to information protection. Sensitivity labels.
This is a crucial distinction. Classifications are what Purview finds. This column contains a social security number. Labels are the persistent, portable tags that enforce policy. A label is a policy statement like highly confidential or GDPR restricted data that travels with the column, file, or asset.
So if a file labeled highly confidential is downloaded from a cloud storage account and transferred to a desktop, that label and all the associated protection policies must travel with it.
That's the core power of Microsoft Purview Information Protection, or MIP, labels. They're managed centrally and provide a unified framework. So whether that data is in Azure SQL, SharePoint Online, or on a local hard drive, the label ensures consistent enforcement of policies like watermarking, encryption, or access restrictions.
Given the sheer volume of enterprise data, manual labeling seems like a non-starter. How does auto-labeling support this framework?
Auto-labeling policies are crucial for scale. You define rules that automate the application of a label. For example, you can mandate. If the content scan detects more than 10 unique credit card numbers, automatically apply the label financial data restricted accesses and encrypt the file.
So it shifts the governance burden from individual users to the automated system.
Exactly.
Let's focus on the database level again. We know Azure SQL has its own classification feature. Where does SQL data discovery and classification fit into this global structure?
Right. Azure SQL provides a built-in classification feature that operates at the column and schema level using metadata attributes. Labels, which define the sensitivity level, and information types, which define the granular data type, like financial or personally identifiable. DBAs can apply these manually with T-SQL commands.
We have to be careful here, though. There are local classifications and global classifications. What is the crucial operational difference?
This is so important. The feature built into tools like SQL Server Management Studio or SSMS is local. Those classifications only apply within that specific database instance.
And Microsoft's recommendation.
Microsoft strongly recommends using Purview for classification and labeling.